Morning, everyone. Welcome to this session, doctoral meeting session on our space science and technology PhD program. I would like to thank you all, our 7 speakers today, and all the audience, including the supervisors, for being here. Today, we're going to be discussing, talking, and listening to the presentation of the PhD students that are working on different problems related to astrodynamics, space tethers, also space debris, GNC problems related to space, etc. Right, so it's quite interesting topic. We have also some industrial PhD thesis, some academic PhD thesis, and I hope you all enjoy. Okay, so sorry for these minutes of delay and these problems with the connections, but I think we are all here now. We're gonna start with Luca and Sadaf. They're gonna be presenting topics on space tethers, right? And then we will continue with Sergio and with the other established before. Okay.
Okay. Hello. My name is Frekhauf, and yes, as everybody else, I'm going to speak about the PhD I'm doing. And it's I'm working on autonomous operations in non-conventional and challenging space with Manuel Sanjurjo and Manuel Soler as my supervisors. So yeah. So what I'm doing is, of course, my operations in challenging space, and I'm going to start with just where I'm come to until this point. So primarily, I will be talking about small bodies, but I will also briefly mention other places. So for the motivation of the research, the exploration of the small bodies in the solar system is quite on the rise now and in the coming future, where we had very recently have had 3, depending on what you define as recently, successful missions to asteroid or comet surfaces, where some of them are also doing a sample return mission, which will come back to the Earth. However, these operations, they provide significant challenges for doing it successfully, not only to taking a touchdown, but also getting a precise enough and accurate enough touchdown to where you actually want to go. And this is due to asteroids. They are so small that usually when you launch a satellite, you don't know where they are. And they are also far in the deep space, so there will be time delays and there will be failures that can happen. And most of this is challenging to predict from in orbit around the asteroid, because you don't know the interior of it without doing exceptionally long observation modes. So there are also similar challenges in other environments, such as with multi-bodies, and hence there are also halo orbits maneuvering, and with also similarly in deep space rendezvous, where you want to say rendezvous with 2 autonomous spacecrafts, but they are too far away to do this from ground control. So the conventional approach for doing these kinds of missions is a very slow one, where you, as I mentioned previously, you select the target asteroid before the mission is usually launched, with some knowledge about the asteroid that you are targeting from ground-based observations. So the Churyumov-Gerasimenov asteroid was actually the shape of that asteroid was actually quite precisely mapped from ground-based satellite observations. But of course, when you arrive there, you will have to do the mapping to figure out the most important things, the gases around it, because of the drag that they can cause, and also the gravity, the gravitational potential in order to do a successful landing. So this is the arrival at target phase, and then when you arrive here, there will usually, for the missions that have been successful now, this phase has been lasting from 1 to 2 years of just satellite orbiting and doing mapping of the surface of, of course, where you want to land, but also to gain enough information about the system or an environment in order to be able to calculate a descent trajectory. And importantly, these are 2 things that I'm going to look at the most. With also, I should have included this lower power as well, because that's also quite significant. But the principle of it is that nowadays, the method this is done is that you do optimization procedure on the ground, where you have all the information about the system, then you calculate your trajectory, and then you do usually a partial ground-based control method where you directly relay the control signals to the satellite or lander from Earth, whereas the lander does some, in Hayabusa case, the lander did the onboard, it did the horizontal plane maneuvering, whereas the vertical plane maneuvering, basically the touchdown part of it, was directly controlled from ground control with, I think if I remember correctly, 40-minute delay of the signal, which is quite significant. So, but moving a little bit back again, why do we want autonomy in the space missions? And of course, if, from what I just said, one of the key advantages is the increased turnaround time and the simplified missions design. Because once you have an autonomous system must be able to handle very many scenarios, and it will simplify mission design. And you will also, since it has to be robust, you will also be able to increase your turnaround time because you don't have to do individual analysis of every single thing that you encounter, because a fully autonomous system should be able to tackle these kinds of stuff. And this requires, first and foremost, robust guidance and control laws. And well, embedded in that sentence, you have the independency from ground-based control. So these satellites should be able to, our landers should be able to get into orbit and successfully land on the surface of the planet or asteroid without any input from ground. Similarly, in also the other scenarios, in halo orbits and or rendezvous case, they should be able to perform the task without having any input from ground-based control. So the possible methods that are available with this is, of course, for the guidance and trajectory part, which is the most challenging part, is you have usual convex optimization, which is the common way to do it, which is either convex or nonlinear optimization is the procedures that are used on the ground for calculating the optimal descent trajectories. But also recently we have seen machine learning or reinforcement learning to be a potential contender to do these kinds of algorithms. But significantly, these methods must be able to, for an autonomous system, these methods must be able to run online on the satellite itself. So shipping off a lander with, say, a machine learning or reinforcement learning algorithm is high risk, since you cannot precisely determine the outcomes of this. You can only, to some degree, you can only say that it will have a certain success rate, but you cannot have any mathematical guarantees for its performance. So this is some key factors, which is what I'm going to be discussing where I go laterwards. And for autonomy, you need, I would say, you need the GNC. It must be able to run on space hardware. You need to have a guaranteed performance. You need to be able to guarantee some certain constraint satisfaction. And you need to have the system to be able to adapt to scenario changes or parameter changes, also if something fails on the system. In a generic fashion, you have this optimization problem that is on the lower part of the screen. Solving this successfully on board the lander or spacecraft is basically how you get autonomy. So the desired goal of my thesis would, of course, be then to solve this kinds of optimization problem using methods that are able to be run on space-proven hardware. And you should be reminded that space hardware in deep space, they have to be significantly radiation protected, so they are often quite weaker. And as a reference, if you know the Perseverance rover, it landed with a computer that was, the control computer was one from the year 2000, similar to one in the Apple iMac. So they are quite slow. So the way the way this problem is usually solved is that you do convexifications and approximations to get a problem that not only gives you a global solution, but also gives you a solution in finite time. And from these convexifications, you usually get a convexifier program, but there are different orders of these kinds of program. And importantly, the lower down the order you get, the faster the solution of these programs get, but the accuracy of the solution or the optimality of the solution is becomes worse and worse. So basically, what I've been doing is that I've been looking, what if you actually use the worst case scenario of this method? which is the constrained linear optimization problem, or also known as quadratic program. The general shape is like this, only with the cost function being quadratic. The advantage of doing this is that this is the most simplistic program to solve, and it's usually used in model predictive control because it's so fast to solve iteratively. I can just briefly mention model predictive control, if you don't know that, is that you solve this problem that is here. You solve that at each time step on the spacecraft with the latest measurements. So basically, you generate a trajectory as often as you can, and then you use the input from this or the thruster configuration that generates from the solution of this optimization problem, and then you apply this, but you only apply the first in the sequence, because then when you iterate one step ahead, you do this calculation anew and you get a new optimal solution, which will then be taken into consideration the new measurements that has occurred. So, but the problem with this is that these kinds of systems need to be robust. So the model predictive control, it has some inherent robustness just because you basically optimize at every time step. So if there are some prediction errors or discrepancies in your model and so on forth, these will get captured by your new measurements, and you will calculate a new trajectory, optimal trajectory. However, in face of bigger uncertainties, and also because, of course, we want to bound the uncertainties, the one method of doing this, or one common method of doing this, is either minimax optimal control or similar quadratic optimal control, worst case scenario basically. But another method that has gained popularity recently is the tube-based method. And this involves using a virtual system, as is the one you see on the right here. And you pretend that this is your real system, which you can see is just a linear system that is able to be solved fast, which is a representation of the true system here, where all the uncertainties are captured, and in this case also non-linearities are captured in this uncertain vector, the omega. And for the uncertain, so what you do is that you want to use the optimal inputs generated from solving the virtual system. But using only this one, you will not get the performance that you want, because this is, of course, lacking all the uncertainty and non-linearities captured in the omega. So what you do is that you need to do some compensation, which is this matrix here, and it compensates for the error. And as you can see there on the right-hand side, this basically captures the actual true system to follow a tube that is centered around the virtual system. So you can consider the dotted line here, the tubes, and the virtual system is, of course, discrete, so it has only two ones. And with these kinds of methods, you can more or less guarantee that your trajectory will lie within a robust positively invariant set centered around your virtual system. And the positively invariant set is defined by these two matrices here, the AK and your uncertainty. And the AK is a design matrix. We basically design how fast you want it to converge. And with this, you have guaranteed convergence to the virtual system. So the advantage of this is, of course, with this, you can guarantee constraint satisfaction as long as you design your parameters correctly. And also, more importantly, is that this is a simple quadratic optimization problem. So it is able to be solved on board and real time, and there already exist very fast solvers for these kinds of stuff. And there's a high degree of autonomy, which I will show later, where you can basically do replanning all over the board should something insane happen. And safety modes is also something that is readily applied to these kinds of methods. However, nothing comes free after all. So the issue with this is that you get a linear performance in a non-linear environment, since you are trying to follow a linear system. And also, as with all optimization problem, once you increase the prediction horizon, the further in you want to look ahead, the more expensive this scheme goes, and also with more dimensions. So in this, the one that I'm presenting now, I'm just using the movements, so only the 6 degrees of freedom. But of course, if you want to extend this to, say, couple it with attitude control as well, then suddenly you get a lot of more degrees of freedom, and the solution of this becomes slower. But and also you get conservative performance, which again comes back to the linear model that you are using. So I'm just going to showcase a quick scenario for a case study. So what you want to do is that we want to land in the center of this asteroid Eros, which is like a banana shape. So basically you want to land in the middle of the bend of the banana without without having any specifically good models of the asteroid or of the gravitational potential field or anything. So as I said, the models that we are using are linear ones, so they do only capture this to a certain degrees. And for this scenario, I've used a just regression of linear regression of a couple of sample points within this domain that has been designed here. And as you can notice also on the image, this domain that I've created goes slightly within the asteroid, but it is due to the construction of this positively invariant set, it will be guaranteed to never be able to collide into the asteroid. And here is some results. And one of the key things with this method is, as you can see on the right here, this is basically the same the initial conditions of the lander in the scenario is randomized with both random velocity and random position at all I think it's 60 different starting conditions here, where all of them successfully manage to land in the exact same spot every single time. It is not, as you can see on the left-hand side here, you can see that the landing accuracy is roughly somewhere between 0.3 to 1.2 meters, which dependent on the asteroid density, because also in these simulations we have simulated the density of the asteroid be changing to plus or minus roughly 40%. So as you can see, the lighter the asteroid, of course, the better precision you get and the less fuel that you're using. However, this, due to the way that we are following a linear model, and also that we have to do compensation for the errors that we gain from following linear model, this method currently uses a lot of fuel, where we use roughly twice the amount of fuel when you compare it to a fuel optimal approach. But also this lands significantly faster because it's you basically thrust directly to the surface as fast as you can go without crashing it, because that's the advantage. As you can see on the, for example, the outer one here, it comes close to the containing box, but it never exits or never crosses it. There are also, of course, some challenges with these methods, and it's a control, since it contains both guidance and control in one simple box. This is susceptible to tuning issues, and as you saw, there are steady state deviations from the accuracy, so it is possible to do some novel or conventional approaches to reduce this one even further and get an even higher degree of accuracy. And a couple of other notes here, but I'm running out of time. So just to discuss on the things that I'm working currently on now is, of course, to improve the underlying models, because now, as I mentioned, I just use a linear model based on regressional analysis. And if you improve your model, you will drastically improve your performance, because the better the model represents the dynamics, the more realistic the virtual environment will be. And of course, the other one, the final part is I want to investigate using this in other environments. And finally, if you can be able to use adaptive model parameters. So if you basically combine this tube robust model predictive control with also adaptive model predictive control to enhance your model as you go downwards. The advantage of this is, of course, that adaptive controllers also have guarantees if you excite the signal enough. So, but this is currently ongoing research. Yeah, that was it for me. So thank you for your attention.